Well, thank you. And thank you for inviting me here to spend time at the Institute, to give some talks, to work with a remarkable mathematician like Raman, and actually to get to know or spend a little time learning about the history and culture of a really beautiful city. When I visit other cities, of course I like to see all the big tourist attractions, the usual things, but I also like to look for small, odd things that to me give a city character. So here's one I saw just the other day. Anybody recognize that, where that is? Anybody know where that is? Yeah. Really? Is it well known? Yeah. I thought maybe it wasn't so well known. I was really pleased when I discovered this. So that's, it turns out, I guess in World War II, St. Petersburg, or at least parts of St. Petersburg, had a real hard problem with rats. And so they put this monument up and because of it. And so apparently you take a coin and you toss a coin up there, and if it lands on the platform that the cat sits on and stays there, you get to make a wish. And I have a daughter who loves cats, so we went looking for it and we found this. And I took a coin out of my pocket and I aimed and I tossed it up. You might notice, see this open window here? Well, that coin sailed up in a beautiful arch and went right in that window. Here, that's where it is, by the way. For those who don't know, those who don't know, there's where it is. And it sailed right through that window into somebody's living room. So the second try, it landed, and I made my wish. By that time, there was a large crowd of people around me, all throwing coins up at this thing. I mean, I was alone when I started, but there were maybe 20 people around me, all of them throwing coins up at this when I was done. It was a lot of fun. My family thought it was so funny that it ended up going through the window that my wife insisted on coming back a few days later and taking another picture. And you might notice that the window was closed. So I'm going to talk about computing homology cobordism classes of manifolds and some special cases of that problem, in particular the problem about trying to classify or say something about concordance classes of knots and links and things like that. So what do I mean by homology cobordism? Well, two manifolds are called homology cobordant if there's a manifold W, one dimension higher, whose boundaries are m and m prime, that they're cobordant as manifolds. Right? You've all seen the picture before. I have m prime, and I have some manifold in between W. So I have some cobordism, right? An n manifold, another n manifold, and n plus one manifold. But they're called homology cobordism. That's not necessarily a product, but if it looks like a product to homology, right? If the homology of the n plus one manifold relative to the n's is 0, then we call it a homology cobordism. So it looks like homology it looks like a product to homology. So you could also talk about this if I have some representation of pi1 of w, it's a map from pi1 of w onto some other group. Then of course I can take the gamma cover, right? If the group have a map to a group gamma, I can take the gamma cover, and I can ask, well, is that cover a homology product? Right? So I can talk about homology cobordism over some group gamma as well. And that also turns out to be very important in studying things about homology cobordism. So the key idea is it looks like a product to homology. Now, by the way, a natural question to ask is, why would anyone care? Why would anyone bother to study this relation? I mean, it's a natural looking one, but why is it so important? Well, it turns out it's important for lots of reasons. It's related to a fundamental problem in knot theory that goes back to Fox and Milnor in the 1950s. They studied this idea of knot concordance, and they studied knot concordance because they wanted to understand things about singularity theory. That is, if I have some codimension 2 submanifold, for instance, and it has a singular point, a point where it's non-smooth, what can I say about that? And it turns out that's closely related to and motivates the definition of the knot concordance group. It's also related to understanding four-dimensional manifolds in general. It turns out I'll talk a little bit about the connection between this problem and also the problem of slicing knots. I'll talk about what that means. And I'll talk about how these problems are related to the question of the classification of four manifolds, or being able to, topological classification of four manifolds. It's related to questions about characteristic classes of non-locally flat embeddings. Turns out that knowing things about the knot concordance group correspond to give you formulae for understanding things about the homotopy type of the classifying space of non-locally flat embeddings in codimension 2, which have of regular neighborhoods of non-locally flat embeddings in codimension 2 with isolated singularities. There's all sorts of very important central geometric problems. It's even related to questions about smoothing theory in four-manifold, because the knot concordance problem tends to be a microcosm for understanding differences between theirs. There's lots of obstructions to understanding when things are not smoothly sliced, but they're topologically sliced. So I'll talk about a few of these things. The two main things I'll talk about as I work through this is a lot about the knot concordance problem and a little bit about four-dimensional surgery theory. So let's talk a little bit about four dimensions. So how did Mike Friedman win a Fields Medal? He proved what's called the disk embedding theorem. So the disk embedding theorem said, well, what he proved was, of course, the topological Poincare conjecture in dimension 4. But that big theorem was a corollary of the disk embedding theorem. And it was always known that if you could solve the disk embedding problem, you could solve the Poincare conjecture. This was the heart of the issue. So what is the disk embedding problem? Well, it says, suppose I have some disk and it's immersed in a four-manifold. And suppose there's some algebraic criteria about the disk. Okay? Now that precise algebraic criteria is written here. It has the property that it has what's called a transverse sphere. There's some sphere which algebraically intersects that disk 0 times. So that means if it comes through in one direction, it comes back through and intersects it at a point again in the other direction. You make them transverse, and it's algebraically 0 times. And it also has intersections and self-intersections 0. Then, with some condition that's hard to define, but pi1 is not too large, if the fundamental group of that four-manifold isn't big in some sense, then in fact that immersed disk can be replaced by an embedded disk with the same boundary. That's the disk embedding theorem. And the solution to that problem is the heart of the classification of topological four-manifolds. If we could understand this in all cases, we would have some sort of a formal classification theory for four-manifolds. But it's only known to be true for groups that are not too large. And even that is a bit of a funny notion, because there's no real definition for what not too large is. He calls them good groups. And what is the definition of a good group? A group is good if this theorem is true for it. Okay? So it's sort of a tautology, except it wasn't. What Mike Friedman did that was so deep is he proved it for simply connected four-manifolds. And that's what he needed to prove the Poincare conjecture. And then later on he said, well, he was able to prove, well, it's true for finite groups. Four-manifolds whose fundamental group is finite. And then he proved it for nilpotent groups. And eventually, along with Peter Teichner, they proved it for sub-exponential growth groups. And nobody knows whether it's going to be true for all groups or not. Maybe all groups are not too large. It's not known. But the conjecture that everyone bets on is this one, that amenable groups are not too large. That the disk embedding theorem works for amenable groups, but not for all groups. And of course, sub-exponential growth groups are getting very close to the class of amenable groups. But there are groups which are amenable, but not of sub-exponential growth. The first were defined by Grigorchuk. These are what are called self-similar groups, groups that are obtained by doing automorphisms of infinite trees using some sort of finite state automata to describe them. And they're a beautiful class of groups. They're groups that have a fractal structure. These groups always have this property that there are copies of the group sitting in itself, deeper and deeper within itself. And that property to me is a very interesting property that I think is going to be related to interesting things about four-manifolds, but I don't know that yet. That's what I believe. So the amenable fundamental groups is so the conjecture is that the disk embedding theorem works for amenable fundamental groups. Now, why is that related to the question that I really want to talk about some today, the knot slice problem, or one of the great questions I want to talk about, the knot slice problem is, well, the connection between this and the question of slicing knots, or links, goes back to an old result of Casson and Friedman. That is, they proved that if the disk embedding theorem holds for four manifolds with free fundamental group, then in particular they can prove that this link is a slice link. Now, I haven't defined slice yet, so let's do it now. Okay? So this says that some question about knot theory, if we could understand it better, would tell us that it would allow us, if we could prove that this link were slice and a few other classes of links that we know about, we could actually classify four manifolds. we could classify 4 manifolds. We'd have a formal classification theorem because the disk embedding theorem would be true. On the other, yeah, okay. So, but if we could show it's not sliced, then we would know the disk embedding theorem is false in particular, right? So what is the knot concordance group? Well, a knot is just an embedding of an oriented circle in S3. And we can add knots. If I have two orientable circles like this, I just put them in separate balls and I draw a little path from one to the other. And then I connect them up along that path in such a way that the orientations work out. I may have to twist the path some, but that's called connected sum of knots. I add two knots. And then what Fox and Milnor did was they said, well, okay, let's take all knots in S3, which are oriented, under connected sum, and we'll define a relation we'll call concordance on knots, which I'm going to define next. And that's called the knot concordance group. You get a group when you do that. It's called the knot concordance group, and it's an abelian group. So what is that group? Or what is the concordance? If I have two circles in this is a schematic drawing. Think of this big square as being S3 cross I. So in this end is a copy of S3. At the other end is a copy of the 3-sphere. And suppose I have a knot down here, which I just drew as a loop here, and a knot up there. Then I say they're concordant if between them there's a cylinder, an S1 cross I, right? An annulus between them. But the annulus itself could be all knotted up. It's not just an isotopy. It's a knotted up annulus in there. But if I can find an annulus with an extra dimension whose boundary are those two knots, I say that they're concordant. Now you can think for a minute, if a knot is concordant to the trivial knot, just a simple loop, that loop bounds a disk. And so I get that the knot you have, in fact, bounds a disk in 4-dimensional space. And that's what it means to be sliced. So to be concordant to the trivial link, we call slice. A knot is slice if it's concordant, or a knot is slice if it's concordant to the trivial knot. And the problem is, how do we determine when knots are sliced? And can we compute the knot concordance group? So this is a very old problem. It's gotten a lot of attention in recent years. In the past 15 years, it's been probably the most worked on problem in low-dimensional topology outside of the Poincare conjecture, I suppose, which was solved.
And what's the simplest sliced knot?
I'll give you an example in just a minute. I don't know if it's the simplest, but I'll give you probably the simplest. I'll give you a very simple one. I guess what is simplest is something that can be complicated to describe in itself, right? But I'll give you an example. Okay? In fact, let me do it now. There it is. That's pretty simple. So you can look at that knot, and it looks pretty clear that you can't unknot it, right? It's essentially embedded in 3-dimensional space. It's not the trivial knot, right? Now you can see a little disk in there that has self-intersections. They're called ribbon intersections. It's like this picture here. Here's a portion of the disk. Here's another portion of the disk. It's like a ribbon, and it crosses over itself so that it comes through itself like this. Right? And that's called a ribbon singularity. And if I have a ribbon sitting in 3-dimensional space so that all the singularities in that ribbon, all the self-intersections are of this type, the knot is called a ribbon knot. And all ribbon knots are sliced. So how do you see that? Well, let me just give you a quick idea of how you see that. Okay? So you can see a disk. The problem is the disk has self-intersections. Right? You can see the disk in there pretty clearly, I hope. But I have this problem of self-intersections. Right? So that disk has self-intersections. So I'll just cut a hole. Now the disk just goes right on through. And now it has no intersections, but it no longer has the right boundary. But all of this takes place in S3, and I can work in S3 cross I. So what I do is in S3 cross I take this circle which lies in S3 cross 0, and I add an annulus going out into S3, right? From if this has points x, y, z, 0, I take x, y, z, t as t goes from 0 to 1. Now I have a circle out here in this 3-dimensional sphere. And now that clearly bounds a disk. Right? So I do that in each of these ribbon singularities, and that gives you an example of a sliced knot. That gives you a slice for that knot. Now one can ask whether or not knots are smoothly or topologically sliced. Right? So smoothly means that the knot bounds a disk in 4 space, and the disk is smoothly embedded. But every knot bounds a topological disk in 4 space. I can just take the cone on the knot. If I have a sphere and I have a knot, I can just cone it inside a disk. But you see, the point is that this point is very odd. It's not nice. In particular, if I take a little neighborhood of that disk, I see a copy of the knot there again, right? So what does it mean what do we mean by topologically slice? Well, we mean it bounds a disk in four-dimensional space such that at every point on that disk, there's a neighborhood of that point that has the topological type. It's homeomorphic as pairs to a standard disk in R3, right? And D3. It just looks like D1 cross 0 and 0, 0 and D1 cross D2. D1 cross the origin and D1 cross D2. It's a standard around any point. I have a disk around any point, right? Say it's locally flat, means around any point there's a little neighborhood such that that neighborhood looks like a standard disk in D3 as the topological type. And so when you're talking about topologically slicing knots, you're asking, does it bound a locally flat disk in D3? Okay. So how is this related to the homology cobordism question? That's what I'm really here to talk about. Well, Capell and Shanison showed many years ago the idea in some sense can be even seen as far back in work of Kerver in the 60s, early 60s. They showed that if two knots are concordant, right? If two knots are concordant, if in fact the difference between those is slice, it's 0 in the knot concordance group, then in fact if I take what's called their exteriors, that is I remove an open tubular neighborhood of each knot, remove an open tubular neighborhood of the knots, then those manifolds I get are homology cobordism. The complements, the exteriors of those knots are homology cobordism, and on the boundary it's a product cobordism. So rel boundary. Okay? So knots are concordant implies that their complements are homology cobordant. And in fact, that's pretty close to being, in the case for, if I'm working on a general 3 manifold, the homology cobordism is over Z pi 1 of the 3 manifold. I take the pi 1 of M covers, and that has to be a homology product. If I'm interested in knots in the 3 sphere, that just means that it's integrally homology cobordant. And that's pretty close in that case to an equivalence. So two knots are concordant and their complex complements are homology cobordant rel boundary. And in particular, if I call C the homology cobordism classes of homology circles, then if I look at the homology cobordism classes of homology circles, that's basically equal to or isomorphic to the group of concordance of knots. Now I have the equal sign in quotes because there's a very subtle difference between them. In high dimensions, if I'm looking at n spheres in n plus 2 space, this statement is true. Concordance of n spheres in n plus 2, the concordance group of n spheres in n plus 2 space is in fact isomorphic to homology cobordism classes of homology circles. It's an open question whether it's true in general because of some subtle point. If I think I'll just avoid talking about the point in any detail, but there's a subtle point having to do with whether or not you get something simply connected. Somehow it bounds a disk in a homology disk as opposed to an honest disk. Can you change that homology disk to a real disk? And if a knot is slice in a homology disk, is it slice in a disk? That's the question. In high dimensions, that's true. In low dimensions, that's still an open question to this day. The bet is that it's going to be false. There's evidence due to work of Cochrane and Horn and I'm just forgetting their names, that's embarrassing, that gives evidence that it's false for smooth concordance. And it's conjectured to be true for topological concordance, but it's an open question. But they're very close to being equal, and they may be equal. So let me give you a little history, ancient history about the knot slice problem, about how to compute the knot concordance group. So let me say what's true about homology cobordism in general. What do we know about computing homology cobordism of high-dimensional manifolds? Well, in some sense, that problem has been solved. That is, it's been reduced to algebra and homotopy theory and problems in related areas where at least one can hope to make the computations for any particular manifold we want to look at, right? And it has 3 steps. So let me just broadly, very briefly outline it. This won't be a detailed explanation, but it does give some starting point for asking how do we how do we solve this problem for knots in 3 space where we don't have high dimensions. Okay? By the way, the difference is in high dimensions, the disk embedding theorem is always true. If I have a disk, a 2-dimensional disk in a high-dimensional manifold, in a 5-dimensional or higher manifold, it's always embeddable just by general position. But in 4 manifolds, I may have self-intersections. That's where things get difficult. Right? That's why things are hard in low dimensions. Friedman's result, the fact that you can embed disks in high dimension is always true. So the first step was Capella and Jameson. They said, well, let's ask this question. Suppose I fix a manifold in, and I consider manifolds that are homology equivalent to in by having a map from M to N. So I fix a manifold in, and I look at homology equivalences of manifolds over N. And now I look at homology cobordism classes of that over N cross I. We'll call that the structure set of N. And then there's a surgery exact sequence that tells you that the structure set maps to some bundle theory, which could be computed by homotopy theoretic things. These are standard sort of surgery theoretic ideas. And it has a kernel, which is some group of quadratic forms, a surgery group, that completely classifies them. So what they did was to actually understand the right form of surgery group for dealing with that. They talked about a homology surgery group, it was called. And that gave a general classification for the problem of computing the structure set of for a fixed manifold. So I'm not considering all manifolds homology that have the same homology groups as N. I'm only considering those that have a map from M to N.
What do you mean by bundle theory?
I mean, it's if you have a map like that, if I have in surgery theory, one has to worry about things about tangential data. In surgery theory, one tries to approximate a homology equivalence or a homotopy equivalence by some map. What does approximating mean? Well, if they were manifolds and had the same homotopy type, then they would have the same bundle theory. In particular, you would have a bundle that pulls back to the stable normal bundle. So the question is, when can you not just find a manifold that looks somewhat like the manifold you want, right? For example, you're going to take two manifolds and you're going to try to construct a homology cobordism between them. So you first take a cobordism between them over N cross I. I find some manifold over N cross I.
Then you're trying to kill.
Then I'm trying to kill the homology groups and make it a homology product. Well, to do that, I need some information about the tangential data on the manifold to be able to embed things in some canonical way, to do surgery. And what that turns into is some problem about having some bundle over the manifold N that pulls back to the stable normal bundle of W. And that's classified by homotopy theory. It's classified by the classifying space of, well, by G mod PL or G mod O, depending on whether you're working PL or O or top. I mean vector bundles, yes. Thank you, yeah. That's right. It's about finding linear reductions of spherical bundles. Finding linear reductions of spherical bundles. Okay? Now, in this language, right, the non-concordance group is just the structure group of S1 cross D2. Right? The classical non-concordance group would be the structure group of S1 cross D2. All manifold, because every knot has a map to the trivial knot complement, which is S1 cross D2. Okay? But in general, you'd like to be able, not just non-concordance, you'd like to say, well, can I find all manifolds of the homology type of N? Well, the next step was some work of Pierre Vogel. Pierre constructed a space out of N. You begin with this manifold N. And what he showed is that there's a direct limit. You could take a sequence of groups homology equivalent to N, such that, which have the property, they're all finite complexes. And he proved that homology cobordism classes of manifolds, homology equivalent to N, is the same as taking the direct limit through the structure sequence through all of these spaces. Right? So you find all the manifolds with maps to N, Ni, which are up to homology cobordism over Ni, and you do that throughout the sequence. The key idea was proving that this sequence of spaces Ni exist. You might call the limit of those N hat, and that's sometimes called the Vogel localization or Vogel homology localization of a space N. Those are finite complexes. And then the third thing was, well, what about embedding theory? And that was a student of his, Jean-Yves Le Dimay. So what he did is he said, well, look, here's the idea. If I have a knot in a manifold M, then if two knots are concordant, well, that means there's a cylinder in M cross I. So there's certainly homotopic as maps into M. So that's one obstruction right there. Two knots in a general manifold can't be, some high dimensional manifold, I have some codimension 2 submanifold K, and if they're not homotopic as maps from K into M, then they're certainly not going to be concordant. But suppose they are. Well, if they are, then you can take the exterior, and the homology localization of that exterior will always be the same, no matter how that knot is embedded. Things about Alexander duality will tell you that the homology type of the localization of that complement will always be the same. However, the map from the boundary of the regular neighborhood of that submanifold in there will differ dramatically depending on the embedding. And so his idea was, so what you really want to do is you fix an embedding, and then you want to look at the structure set of the pair. And then there's a pair for every, right, where that's the boundary of the regular neighborhood of K. And there's a pair for every possible homotopy class of maps. Okay, let's get down to it. Of this boundary into the localization of the exterior. So the remaining invariant that Liddy-May discovered was take a look at the exterior of the knot, take its localization, and take the homotopy class of the boundary of the exterior of the knot in that. And that's the remaining invariant that you need to classify high-dimensional homology cobordism. Now, it doesn't matter if you followed that or not, because it's just a little background. I want to get across the idea that this problem in some formal sense has been completely solved in high dimensions. Embedding theory is known up to homology cobordism in higher dimensions. But in the classical dimension, it's very much open. Now, these invariants of Liddy-May have appeared in all sorts of things that you may or may not have heard of. For instance, Haflicker's classification of high codimension links was done using an invariant, which we now know to be a special case of Liddy-May's invariant. This is work in the 60s. Milnor's invariants, Milnor's mu-bar invariants that he defined actually was part of his bachelor's thesis. Been seminal work, years. There's still tons of work being done studying Milnor's invariants. Very important product invariants. Also, Massey products in the of one-dimensional cohomology classes in the exterior of the knot. That's equivalent to Milnor's mu-bars. Those are special cases of Liddy-May's invariant. Something called the Soto-Levine invariant. I think I won't talk about that. Liddy-May himself used this invariant to classify links of even-dimensional spheres of codimension 2 up to concordance. That the concordance classification of even-dimensional links is given entirely by Liddy-May's invariant. It's a complete classification. The surgery theoretic side of things is 0. There have been a lot of recent work. Prudence Heck did things on knots and prime 3 manifolds. A guy named David Miller talked about Milnor's invariants and fiber 3 manifolds. A woman named Carolyn Otto did some very nice work studying links, and they're all analogs that they used of special cases of the Liddy-May invariant. So it's been quite influential in modern knot theory. Now I want to talk about knots in S3. So what I want to do is to take that high-dimensional theory, push it down into dimension 4, and ask where things get complicated. What can we say? So I want to figure out the structure group of S1 cross D2. Okay, so we're going to use the idea I said before. We're going to construct just some manifold between M0 and M1. It'll be a spin manifold. We'll add an extra condition on it that'll allow me to get some sort of framing issues. And then I'll try to do cut and paste to make that a one-dimensional homology equivalence. And then I'll ask, well, can I find 2 spheres representing the 2-dimensional homology of the pair that I can excise using surgery theory and get rid of the 2-dimensional homology? If I can do that, then what you hope for, then you know that the 2-3 manifolds will be homology cobordant. And what you'd like to do is what you'd hope is that the obstructions to being able to do that would lie in one-to-one correspondence roughly to homology cobordism classes of 3 manifolds. That's the basic idea. Now, once again, Friedman's disk embedding theorem becomes the central point. If I have a 2-sphere in 3-dimensional space, I can only immerse it. I can't embed it. It's not in 4-dimensional space. I might have certain self-intersections, right? So in this picture, A, you can see the surface A. It folds around and back. Suppose that's part of a sphere. And suppose that B is part of the same sphere or possibly a different sphere. Right? Then why is the disk embedding theorem useful? Well, suppose I can find an embedded disk. Suppose I can find some embedded disk that you know, I take a line in one part of the surface from A to B and a line in the other part of the surface from A to B. And suppose I can find some embedded disk there. Well, then I can just push that sphere along that embedded disk, as you can see, until it just wraps around there and it no longer intersects B. I can remove pairs of intersection points. If I can algebraically find them in canceling pairs, I can remove them. The problem, so algebraic data is sufficient to tell me when I can find an immersed Whitney disk. That's called a Whitney disk. Right? So algebraic data is sufficient to tell me I can find an immersed Whitney disk. But I need Friedman's theorem to tell me when I can take that immersed Whitney disk and make it embedded. And Friedman's theorem isn't known to work for all groups. If I can make it embedded, then I can separate the spheres by the Whitney trick and get embedded spheres. Right? So the problem is the failure of the Whitney trick, how I make those immersed disks and make them embedded. And the trick that goes back to Casson is I take an immersed disk and I find that I can take all those intersection points and pair them up. So I can find immersed Whitney disks. And then he says, okay, but the immersed Whitney disk is also immersed. But maybe I can pair up intersection points on that and find more Whitney disks. And maybe I can pair up intersection points on those Whitney disks and find more immersed Whitney disks. And Friedman's idea that goes back to Casson is, well, if I can do this infinitely many times with enough control on how it's done, then magically there's this topologically embedded locally flat disk contained in a regular neighborhood of a compactification of that tower of Whitney disks. Okay? So that was a motivation that Peter Teichner and Tim Cochran and I used several years ago. We defined what we call a knot to be k-solvable. So a knot's k-solvable if you can find a manifold W whose boundary is zero surgery on the knot. Its boundary is the three manifold that looks that whose right. You take. Let me just draw it a little. I have some sphere, and I have some knot in my sphere, which I'll draw as a zero sphere schematically. And suppose it bounds some disk in the 4 ball. And then I remove some regular neighborhood of that. Then the new boundary looks like the 3 sphere minus a neighborhood of the disk, minus some neighborhood of the knot rather. Union, well, what do I have here? I removed S1 cross D2 and I'm replacing D2 cross S1, and that's called zero surgery on K. So I'm trying to find a 4 manifold whose boundary is zero surgery on K, and if you check, that 4 manifold has the homology of a circle. So if I'm trying to slice a knot, I'm trying to find a 4 manifold. I'm trying to show that zero surgery on the knot bounds some homology circle. So I say, okay, I choose some 4 manifold that bounds, say a spin 4 manifold. There's only a Z mod 2 obstruction to finding a spin 4 manifold, the RF invariant. And then I want to find one such that H1 is Z. That's easy to do too. It's just the RF invariant to find that. And once I find that, now I take a look at the second homology and I try to represent it by immersed spheres. And if I can immerse those spheres and then pair those points up, the black one is my immersed sphere. Now I pair up a set of points, all the points in pairs, and I let those bound immersed Whitney disks. And then I pair up points on those immersed Whitney disks and let them bound immersed Whitney disks. That's the red. I have 2 towers now. 2-height tower. And then I take those and I pair them up and I do a 3rd tower. We call it k-solvable if I can do that k times. So you call, if you can find that 4 manifold such that the homology in the second dimension is spherical and has this k-fold tower of Whitney disks, we call the knot k-solvable. And the k-solvable knots form a subgroup of the knot concordance group. There's the 1 solvable knots, the 2 solvable knots, all the way down until you get to the intersection of all of them, and that contains the slice knots. Now there's a technical point. They may or may not be equal, it turns out. I don't think I'll dwell on that, but that's a very good approximation to a slice knot. And you take a look at this filtration on the knot concordance group. Now let me tell you some of the history of what people have done in the past and how it relates to this filtration. So in the 1960s, Levine classified higher dimensional knot concordance. And when he classified concordance of higher dimensional knots, all the invariants he defined worked for knots in S3, but they didn't classify knots in S3. Well, it turns out the high dimensional knot concordance group is isomorphic to the group of all knots modulo the 1 solvable knots. We showed that. Casson and Gordon to find new invariants that are called the Casson-Gordon invariants back in the 70s. And they were shown to give you examples of knots for which Levine's invariants vanish but were not slice. Well, we proved that if a knot is too solvable, then the Casson-Gordon invariants vanish. Okay? So Casson-Gordon invariants were invariants of the quotient 1 solvable modulo 2 solvable knots. Friedman in the 80s proved that, in fact, knots with Alexander polynomial 1 are slice. It was a corollary, a fairly easy corollary of the disk embedding theorem once again. And then in 2003, along with Cochrane and Teichner, we defined this filtration, and we showed that the very next term was non-zero. So that would never, right? Nobody had any invariants that could see beyond the second term of the filtration. And then later, Cochrane and Teichner were able to show that they're all non-zero. All successive quotients in that filtration are non-zero. And finally, in 2009, Cochrane, Harvey, and Leidy began to uncover an interesting structure theorem that tells us something of what these quotients might look like. So we made a lot of progress in understanding this is topological. Well, this is also true smoothly. The quotients are the smooth and topological concordance group have the same relative quotients here you can prove. The difference between them would have to be the question of when topologically sliced knots are not smoothly sliced will be the difference between the smooth and the topological category. Okay, so there's the filtration, and Cochrane and Harvey and Leidy had a conjecture that, in fact, the knot concordance group has the structure of a fractal set. That is, that it contains copies. They showed that it contains many copies of the knot concordance group within it. And they tried to find, they're trying to see, so conjecturally it is a fractal set. Contains infinitely many descending copies of itself. I don't know if that's true or not, but I think there's a pretty good bet that it is. It's a beautiful conjecture. So what did Cochrane and Teichner and myself do to prove this result, that these filtrations were non-zero? Well, we introduced something called we introduced Cheeger-Gromov invariants, analytically defined invariants that are related to L2 signature theory. So we brought some analysis into the picture. So that was part of what we did. I mean, defining the filtration was a big part of it. Understanding something about the calculus of Whitney disks, Whitney towers was a lot of it. There was also questions about refining intersection theory, Poincare duality and intersection theory, and linking theory to deal with higher solvable covers of manifolds. But big part of it was, in fact, the study of Cheeger-Gromov invariants. So what we showed is if I have a manifold W, it's a homology cobordism, and suppose that W has some sort of a map to a group gamma, which is called a polytorsion-free abelian group. All that means is the group gamma has a finite sequence of subgroups such that the associated quotients are all abelian. A free abelian, torsion-free abelian, rather. Okay? That's called a polytorsion-free abelian group. In any group like that, then if you have a representation of pi1 of W into that, then the associated Cheeger-Gromov invariants, which I'll give you some idea of what they are in a minute, will have to vanish. That is, that rather the Cheeger-Gromov invariants of one end of M0 and M1 will agree. So if I have M0 and M1 and I have a map to gamma, I get Cheeger-Gromov row invariants, and they would agree if they differ by some 4 manifold over gamma, which is a homology cobordism.
What's an example of this gamma?
Well, polytorsion-free abelian groups are very easy to construct. You could take any solvable group, and then you can associate to it something called the rational commutator series, which just gets rid of all the torsion. And now you have you take the rational commutator series of that, and you take the sequence of derived subgroups, and that will do it. So you just mod out by the intersection of the rational lower central series, and lots of groups like that. They're all over the place. Free nilpotent groups are examples. There are lots and lots of them. They're easy to find, very easy to find. So in particular, there were plenty for us to show that everything in this tower is non-zero. Every step of this tower was non-zero. Over time, we were able to show that. Okay. So what are the Cheeger-Gromov row invariants in the L2 index theorem? What's that? So I'm going to give you a definition of these, but first let me talk a little bit, at least of some sort of a definition. But first let me talk about von Neumann algebras in L2 dimension. Suppose I have a discrete group, and I can take little L2 of that group. That is the square summable terms over the complex numbers. Right? I just take power series, or power series in I take infinite sums alpha in Gn, where Gi's are elements of that group, and I just have that the coefficients have finite length. And then I can take the bounded linear operators on that, an L2 of gamma. Right? The bounded linear operators. The group von Neumann algebra of gamma are just those operators which compute with left multiplication of gamma on L2 of gamma, right? So I take the bounded linear operators which commute with a left operation of gamma, and that's the group von Neumann algebra. And the great thing about the von Neumann algebra is that modules over the von Neumann algebra, even though they're infinite dimensional as vector spaces, the von Neumann algebra is infinite dimensional as a complex vector space, you can still find some notion of dimension for modules over a von Neumann algebra. That is, there's a trace operator on a von Neumann algebra, and that allows you to define the dimension of a module over the von Neumann algebra. It's called the L2 dimension, and it satisfies the types of properties you want it to satisfy. It's finite if M is finitely generated. On a one-dimensional free module, it has dimension 1, and the zero module has dimension 0, and it's additive. Right? In particular, this condition will imply, right, if I have a short exact sequence of modules, then I get additivity like I would expect on dimension. In particular, the k-dimensional free n gamma module would have dimension k. But this is a real valued notion of dimension. Right? The dimension of the von Neumann algebra is not an integer. It's a real number. But it's great because it allows us to talk about dimensions of when the vector space is infinite dimensional over the complexes. So what do I mean by the? So suppose I take a complex. Suppose I take a CW complex and I take some representation to a group gamma, and I take the homology with coefficients in the von Neumann algebra. The dimension of that is called the L2 Betti number of the space. And I can talk about L2 signatures too. If I have an intersection pairing, sort of a classical intersection pairing, but with n gamma coefficients, then I can take that and I can break it up into a positive, a negative, and a zero-dimensional vector space using the function calculus. And then I can talk about the dimensions of the positive and negative eigenspaces, and that gives me a real valued signature. Now think about this. Suppose gamma is an infinite group. Right? Gamma is an infinite group. Then n gamma is an infinite dimensional vector space. So you can't talk about classical signatures for something like that, because what do you mean by the signature of something which is an infinite dimensional vector, a form on an infinite dimensional vector space? But you can't talk about von Neumann signatures, because you can make sense of this as a module over a von Neumann algebra where you get a real valued notion of dimension. So now suppose so I'm going to give you a definition of the Cheeger-Gromov invariant, which really is not an analytic definition. It's going to use the L2 index theorem to tell us how it's related to the L2 signature. I'll give you a signature theoretic definition of the Cheeger-Gromov row invariants, okay, which are analytic invariants. So I take a 4k minus one-dimensional manifold, and I have some homomorphism to a group G. And then Thurston tells me that group G embeds it in a cyclic group. If it embeds in an acyclic group, well, the bordism of the 4L minus 1 dimension bordism of the 4L minus 1 dimensional bordism of 4L minus 1 dimensional manifolds is finite. So in particular, it's rationally trivial, which means I can take a multiple of the manifold, and since that's an acyclic group, it's like bordism over a point. So some multiple of the manifold bounds over KH1. And then I can take the L2 signature of that, subtract off the classical L2 signature of W, divide by K, and I get a notion called an L2 signature of M. And the L2 index theorem tells me that L2 signature of the 4 manifold is equal to the Cheeger-Gromov invariant of the 3 manifold. So the key thing is that if the group gamma, if the group G, if I'm looking at if I have a homology cobordism over a group G, where G is a polytorsion free abelian group, then I get a homology cobordism invariant. And that was how we proved that all these different, we used those homology cobordism invariants to show all these different quotients of this filtration was non-zero. But more generally, you could ask, well, okay, but when is a Cheeger-Gromov invariant a homology cobordism invariant? For what groups G? If I have a map from pi 1 of m to G, and I have a homology cobordism over G between two manifolds, when will I get the same invariant, Cheeger-Gromov invariant for both manifolds at the end? Okay. And that we answered that. We improved the theorem that we originally used. Jae-Chun Cha and I proved the theorem we originally used about polytorsion-free abelian groups. We proved that if I have a group G which is amenable, and I have some quotient of G, and the kernel is what's called a D group. It's some homological condition on the group. Then, in fact, homomorphisms over that group, or homomorphisms to that group, give me homology cobordism invariants over the group. So I can use that, for instance, to define invariants of non-concordance, or things about three-dimensional homology cobordism of three-dimensional manifolds. So not only that, are the row invariants equal, so are the L2 Betty numbers. Okay. Now, what groups does this work for? Amenable D groups? Well, let's see. The polytorsion-free abelian groups that we used in our original work are all groups for which this theorem holds. It generalizes the best previous theorem. Other examples, let's just say that there are all sorts of automata groups which are not polytorsion-free abelian. They're not solvable. Nonetheless, they have intermediate growth. And yet they're amenable D groups. So there are lots of groups we can use that haven't been done before. I'm going to give you one application to finish up my talk. It's not going to be about knot concordance. I have 9 minutes here. It's not going to be about knot concordance, but it's going to be about homology cobordism of three manifolds. So this is, again, work with Jae-Chun Cha. So we'll prove that I'll give you an outline of a proof that there's a sequence of hyperbolic three manifolds, all of which are homology cobordant, all with maps over a fixed manifold M, with a property that no two of them are homology cobordant. Okay? And this sequence of three manifolds will have the property that no previously known obstructions would see that they're not homology cobordant. Okay? So let me talk about how you do that. Okay? All previously known invariants vanish for these. So begin with just a torus bundle over a circle. So we'll take S1 cross S1, and we'll take the mapping cylinder. Let's see, what are we going to do? We're going to take we'll take the mapping cylinder of S1 cross S1 that you get by doing multiplication by the antipodal map on both S1, or multiplication by -1 on both S1s. Multiplication by S1 on both S1. So that gives me a torus bundle over a circle. And the fundamental group of that torus bundle is this group which I'll call Z squared semi-direct product Z. I put a little T to mean twist. The action of Z on each factor Z is given by negation. Okay? That's the fundamental group of that torus bundle. Now, you can show that there's an extension of this. You can compute things about two-dimensional homology and use the classification of central extensions. And you can show this has a central extension by the group Z mod 3. So and in fact, Z mod 3 is in the intersection of the lower central series of this group. So in fact, this is a group, you could talk about the transfinite lower central series. This is a group which has a transfinite lower central series of length omega plus 1. Right? It's not, the intersection of the lower central series is trivial, and the it's still a transfinitely residually nilpotent group, and this Z mod 3 is in the kernel. In the intersection of that lower central series. And let's consider that group G. It has a map down to Z squared semi-direct product Z, and it induces an isomorphism on the lower central series. Now let's take a generator of that element in Z3. Okay, now that's an element, as I said, in the intersection of the lower central series of G. Okay, now what I'm going to do is I'm going to use that class to somehow alter my three manifold to a new three manifold, which is homology equivalent to the original one, but isn't homology cobordant to the real one. Okay? So how do I do that? Well, the first thing I'm going to do is I'm going to increase the size of the manifold M. I'm going to do some homology cobordism to some new manifold, three manifold, such that the homology cobordism maps on, the fundamental group of the homology cobordism maps onto this longer group. And that's sort of straightforward to do. One can set up a system of equations that tell you how to add 1 handles and 2 handles. So you find some system of equations that describe something about this element gamma. Let's see, gamma is part of a solution set to some system of equations that you can define over the original group. These CIs are words. They're commutators in these YIs. So there's some such system of equations that have a solution in the original group you can prove, and for which gamma is part of that solution set. And now what I do is I add 1 handles and 2 handles to my 3. I take my 3 manifold cross I. I add 1 handles for every generator, for every YI, and I add a 2 handle to kill the relation YI is equal to this original element GI times the commutator. So I'm adding 1 handles and 2 handles. Right? So I don't know how clear that is. I take my 3 manifold, I cross I. Now I add a bunch of 1 handles. I add it for every YI, I add a 1 handle. Now these GIs are words in the original 3 manifold. And the YIs, well, they represent these, right? The GIs are some elements in pi 1 of the 3 manifold. And and I have these curves which represent for me the YIs now. And so I just take the word YI times C1 inverse G1 inverse, Y1 times C1 inverse G1 inverse. That's some curve that wraps around over the top end of this, and I add a 2 handle. And I do that for each of those. And then you compute, and you see that what I've done is created a 4-manifold homology, which is a homology cobordism between some new 3-manifold and the one I started with. Now what I want to do is to change that 3-manifold somehow. I want to change it. I want to get something new. So to do that, I take a knot, which has the property that its ARF invariant is 0. But it has the property that the intersection of these classical signatures, you have a signature associated to every, knot theory gives you a signature associated to every complex number on the unit circle. And I take that and I integrate those over the entire circle, and I want something for which that's non-zero. That turns out to be a way to compute a certain L2 signature for that knot. Okay? And then I take that and I now change my 3 manifold by choosing some curve in the new 3 manifold. Down here I have my original 3 manifold. Let's see, what am I doing? I have M1. I choose a curve in M1. Let's see, did I start off with M1 or M0? Let me be careful. Okay, I start off with, I'm sorry, M0. So now I have this new manifold, I have M0 down at the bottom, and I have this new manifold, 3 manifold I call M1 at the top, which is a homology cobordism to it. And now I find some curve in that new 3 manifold representing this element gamma that I chose. I have a map from this into this group gamma, and I find some curve up here in this new 3 manifold that represents that. And now I do surgery on that. Okay? So what I do is I replace a regular neighborhood of that knot with the exterior of the new knot. Right? I take that curve, gamma, I take a regular neighborhood of gamma, and I remove it. So I removed a homology circle. Remember, the exterior of a knot is another homology circle. So I take my new knot K that I created that has this interesting L2 signature, and I place that inside. I replace the old knot with that, and I get a new 3 manifold. And then I show that new 3 manifold I get is, in fact, I can construct a 4 manifold whose boundary is the original manifold M0 together with that new 3 manifold. And then I compute the L2 signature of that, and using standard techniques that we developed in previous papers, you can actually show that that's a non-zero L2 signature. But by the amenable signature theorem, that L2 signature has to be 0 if those 2 3 manifolds are homology cobordism. Okay? That's the idea. And then you have to worry about, well, what about previous invariance vanishing? Well, it's a little exercise to check that it follows from basic facts. For example, let's see. The fact that the Heegaard-Grobov invariance associated to representations to any torsion-free group. So such as PTF groups, have to vanish is because gamma is a torsion element. So it'll map trivially to any torsion-free subgroup. And the fact that invariants vanish for given any PTFA group, any polytorsion-free abelian group, you have a map to that, then that curve has to vanish because this lies in the intersection of the lower central series. But any PTFA group you could prove, which is a quotient of this group, has to be solvable. Well, it has to be not solvable, but has to be residually nilpotent. So gamma has to go trivially into it. And those are enough to show that, in fact, all previously known invariants vanish. I think I'm out of time. I was going to say a little bit about some recent efforts of work I'm doing on four-dimensional surgery with Mark Powell, but I think I'm not going to go over. Thank you.